In this presentation, we are going to learn about the numerical which are based on to the units of time. 360 degrees is equal to 24 hours. So this gives us a factor of 15. So when you measure this angle in degrees, you divide it by 15 and you will get the LST in the units of time also, hour, minutes and seconds. So this is the definition of local sidereal time. Westerly hour angle of Aries measured from the observer's meridian. Let's now go into our first question based on the rational horizon diagram. The question says, during morning twilight, an unknown star bore south with a altitude of 40 degree 20 minutes. During evening twilight at LST, local sidereal time, 3 hours 34 minutes and 24 seconds, the same star bore north with a altitude of 13 degrees 08 minutes. Identify the star. Now, before we start solving this question, I would like to explain to you the basic concept or the basic procedure which we follow in all these celestial navigation based questions. Now, the basic thing to be done is, number one, draw the rational horizon diagram. Whenever you get such a question based on principles of navigation, you draw the rational horizon diagram. And in that rational horizon diagram, you try to fit in all the required information which is given to us. So whatever information is given, a particular celestial body, its bearing, its altitude, or any other information, we try to put in that particular diagram. Now, as we put all this information in the rational horizon diagram, the diagram itself tells us or leads us to the solution of the question. In most of the cases, the question can be solved using spherical trigonometry. You will have a PZX triangle formed, and you can use the spherical trigonometry cosine formula or Napier rule. One of them will be applicable in that triangle, and by applying these formula, you will be able to solve the question easily. So this is the basic concept which we use. Make the rational horizon diagram, put all the information what is given to us in the question, and we will get a lead from the diagram itself how the question needs to be solved. Either it will be a very simple calculation, just adding or subtracting some values, or it will be a solution of the PZX triangle using the cosine formula or the Napier rule. Now let's try to check this concept, whether the concept works or not in this particular question. Let's fit these things one by one. We will first make the rational horizon diagram. So you make a circle and you show these 4 points representing the directions: north, east, south and west. NESW, these 4 points are shown. Now at the center of this circle we have the zenith. So we can join N and S, we can join W and E. The point of intersection gives us the center of the circle, which is the zenith. So the center of this diagram represents the zenith of the observer. The circumference represents the rational horizon of the observer. Now let's try to put all the given information in this particular diagram. Now they have told us that during morning twilight the star was bearing south. Now south bearing in this diagram is represented by this line ZS. ZS represents south bearing. The point S is on the rational horizon with altitude 0. The point Z is the zenith of the observer with altitude 90. So our star was bearing south. That means it has to be somewhere on this line ZS. So star bore south with a altitude of 40 degree 20 minutes. So our star, which is on line ZS, has a altitude of 40 degree 20 minutes. Now we know the radius of this diagram is 90 degrees because its center is zenith, the circumference is rational horizon. Every point on the rational horizon is 90 degrees away from the zenith. So the radius is 90 degrees and the altitude of the star is 40 degree 20 minutes. So that means it is 40 degree 20 minutes above the horizon. Now on this line ZS, S point represents the horizon. If you go 40 degree 20 minutes away from it, this is the location. 40 degree 20 minutes away from the horizon, this is the location where the star is. So we have shown the star's position at the time of morning twilight, and let's mark that position as X. Further, the question says during evening twilight at LST so and so, the same star bore north. So north bearing represented by Zn. The star had a altitude of 13 degrees 08 minutes. So it was 30 degrees 08 minutes from the horizon. Now N point represents the horizon here. So if we go 13 degrees 08 minutes above the horizon, this is where the star is at the time of evening twilight. Now we have the location of the star at the time of evening twilight as well as at the time of morning twilight. It is the same star. Now the same star can be at these two locations, that is X location in morning twilight and X dash location in evening twilight, only in one way. Its declination circle has to pass from both these locations. The star always remains on its declination circle. And there is only one way a circle can be drawn passing from these two positions. How can we draw a circle? The circle can be drawn in this particular way only. So this circle, which is passing from X and X dash, represents the declination circle of the star. Now we are aware that at the center of all declination circles is the pole. So let's mark off the center of this particular circle. The center will be north of Z because you see SX distance is 40-20, which is much greater as compared to NX dash, which is only 13.08. So the circle is offset to the north. The center will be north of the zenith. And the center of the circle has to be the pole. We are aware that all the declination circles are centered at the pole. Now the star will be moving in this particular direction marked by these green arrows. This is how the star will be moving. We can also show the equinoctial in this diagram. Equinoctial is 90 degree away from the pole. So you go 90 degree away from the pole and this point is the Q point from where the equinoctial is passing, and equinoctial always passes from the west and east points. So this blue color line which you see in the diagram now represents the equinoctial WQE. So now beta, before we proceed further, any doubts coming to your mind up to here?
Yes, sir. Sir, how did this equinoctial come so down, sir?
Okay, beta. Beta, one thing is that equinoctial will always be in a direction opposite to the pole. So अगर आपको यहाँ पे north में pole दिखाई दे रहा है तो equinoctial south में होगी. That's one thing, right?
Yes.
And second thing, the equinoctial Q point of the equinoctial is always 90 degrees away from the pole. In fact, all the points are 90 degree away from the pole. But for understanding, always remember this Q point will be 90 degrees away from the pole, right?
Right.
And we also know that the radius of this circle is 90 degrees. So we get an idea of how long 90 degrees is. So from point P, you go 90 degrees towards south. That is how you identify point Q.
Okay. Understood.
Okay, beta. Any more doubts, beta?
And this PZ is equal to QS, right, sir?
Exactly, beta. PZ, Papa to Zulu, is always equal to QS.
सर पोल पी को एक बार एक्सप्लेन कर दीजिएगा सर.
Pole को explain, beta, means how did the pole come here?
Yes, sir.
Okay.
This center of the this new circle or what?
बेटा पोल इज द सेंटर ऑफ ऑल डेक्लिनेशन सर्कल्स. हमने पहले तो यहाँ पे डेक्लिनेशन सर्कल बनाया है यूजिंग द इंफॉर्मेशन विच इज गिवन. एक बार सर्कल हमारे पास आ गया तो जो भी उसका सेंटर आएगा वो पोल होगा. सो दैट्स हाउ वी आइडेंटिफाइड द पोल. ओके बेटा, गॉट इट?
Yes, sir.
ओके, ग्रेट. एनी मोर डाउट्स बेटा? Great, beta. Excellent. So let's proceed ahead. Now the LHA Aries is obtained from the value of local sidereal time. As I told you, local sidereal time is the westerly R angle of Aries measured from the observer's meridian. And this is in the units of time, 3 hours, 34 minutes and 24 seconds. As I told you, we can easily convert it into angular units by multiplying by 15. So we multiply this LST 334.24 by 15 and we get a value of 53 degrees 36 minutes. So this 53 degrees 36 minutes is the westerly R angle of Aries measured from the observer's meridian. And this is the definition of LHA Aries. In fact, if LST is given to you, if you convert it into angular units, it gives you the LHA of Aries. LHA of Aries is the angle at the pole contained between the observer's meridian and the celestial meridian of Aries measured westwards. And this is exactly what LST is. So multiplying the LST by 15, we get the value of LHA Aries, which is 53 degree 36 minutes. Go ahead, beta.
Sir, do we need to mark the LHA Aries on this Rashmi notation, sir?
करेंगे बेटा, अभी मार्क करेंगे.
Okay.
Okay. Now let's show this value in our diagram here. The observer's meridian is represented by PZQS. This particular line represents the observer's meridian. Now LHA Aries is 5336. So from the observer's meridian, if I draw an angle of 53 degree 36 minute, this is where the meridian of Aries would be. So from the observer's meridian, we go in the westerly direction. You see, this is the westerly direction by 53 degree 36 minutes, and it gives us the celestial meridian of Aries. This is the location where Aries is going to be.
सर ये जो हमने 53 डिग्री मारा, ये हमारा तो 53 में दिखने में मोर देन 90 लग रहा है।
नो प्रॉब्लम बेटा, आप इसे छोटा बना लो, नो इश्यूज।
ओके ओके, मुझे लगा आपने किसी पर्पस के लिए मारा है। ओके ओके।
No, 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 no. You can make it smaller also. I've just made it for clarity. That's all. That's all. Now you see, we can find out the westerly R angle between Aries and star X. Now when Aries was at this particular location at the time of evening twilight, the Aries was at this particular location and our star was at the location of X dash. So Aries is at this particular location, the celestial meridian of Aries represented by P Aries, and the star is on this particular celestial meridian, the celestial meridian of the star represented by Px dash n. Now we can easily measure this particular angle, the green color angle in the diagram. What is this green color angle? It is the angle at the pole contained between the celestial meridian of Aries and the celestial meridian of the star. And this is the definition of SHA. So the SHA of this particular star can now easily be found. You can see from this point, you can follow the laser pointer, from this point up to this point is 180 degrees. This is the angle between the observer's meridian and his inferior meridian. So this total angle is 180 degrees. The maroon color angle is 53 degree 36 minutes. So the green angle has to be 180 minus 53 36. That gives us the value of 126 degrees 24 minutes. So we get the SHA of this particular star. The SHA of the star is known. Now what we do is, you see we have this NX dash arc known to us. It is 13 degrees 08 minutes. We have the SX arc also known to us. It is 40 degree 20 minutes. And we are aware that from point S to Z is 90 degrees. Z to N is again 90 degrees. So this total N to S is 180 degrees. Now if I subtract 1308 NX dash and SX 4020 from 180, I can get the diameter of this particular circle. So 180 minus 13 degrees 08 minutes minus 40 degree 20 minutes gives me the diameter of this circle, which is XX dash. Now if I divide the diameter by 2, I get the radius of this particular circle. The radius of this circle is Px dash. Now this radius of the circle which I am getting is basically the polar distance of the star. This is the pole and point X or point X dash is the star. So Px or Px dash, both representing the radius of the circle, give me the polar distance of the star. Now we know 90 minus polar distance gives us the declination of the star. So once we calculate Px, you see this is the value of Px here. We know pole to equinoctial is 90 degrees. So 90 minus Px gives you the declination of the star, which in this case comes to be 26 degrees 44 minutes. So we get the declination of the star 2644. We get the SHA of the star, which is 126 degrees 24 minutes. With these two values, we can now go into the star information table on page 268 and we can look for this particular SHA. And from there, we find out that this particular star is Alpha, having this given SHA and declination.
Sir, declination
Can we possibly? Can we
Go
work
ahead.
out this excess dash because I'm getting some different answer for
Sure,
excess
beta.
dash.
We can just punch in the numbers in your calculators. 180 minus 1308 minus 4020. What are you getting?
Correct, sir.
126 degree 32 minutes.
Yeah, sir.
मिल गए बेटा? Value got?
Okay, yes, sir. So I by mistake and then subtracted from 180.
Okay, no issues. So you got the answer now, right?
Yeah, then divide by 2.
That's right. That will give you polar distance. 90 minus polar distance gives you the declination.
Sir, declination will be QX also, no? We can say QX will be also declination, sir, correct?
Exactly, beta. QX is the declination. You are right.
और सर QX X dash और जो ऊपर का है सर वो
That is
evening
nothing, beta. There is nothing. You are
Polar
basically
distance,
going
PM.
on other side of the pole. Q to X dash, you are going to the other side of the pole.
Okay, sir. Okay, sir.
Okay, sir. How to find the star?
You got the SHA and declination, right?
Yes, sir.
Now you open up the almanac, beta. Go to page 268. If you have it, just open it up.
Yes, sir.
Now in page 268 table, look for a SHA of 126. That's what we got. So it is the stars are given in serial order of SHA. So start from first star, go up to SHA 126. What do you get there, beta?
Alpha, sir.
Great, beta. You got the answer. 25 marks.
सर एक स्लाइड बैक जाना सर वो स्क्रीनशॉट लेना था.
Okay, beta, we will go back. But the entire question is there. The solution is there. I'll go back. Don't worry. Any more doubts, beta?
Sir, one doubt, sir. This red line is not a declination, right, sir? Red one is celestial meridian passing through Iris, right, sir?
Yeah, that's right, beta. The red line is basically representing the celestial meridian of Aries.
Okay, sir. Okay.
Okay, great. So no more doubts, beta? Very good. Let me go back one slide now. Just a minute. Here it is, beta.
Okay, thank you, sir. हो लिया.
Okay, great. So shall we move ahead, beta, to next question?
Yes, sir.
Okay, let's go. Let's now move on to the next question. On 13th of October 1992, in latitude 62 degrees 30 minutes north, star Vega bore 270, and at the same time, an unknown star bore north with an altitude of 34 degrees. Identify the unknown star. We will follow exactly the same approach in this question. That is, we will make the rational horizon diagram and we will feed or input all the information what is given to us in the question in that diagram, and the diagram will give us a lead. So let's put all the information in the rational horizon diagram. We have the rational horizon on the screen now. We can show the NESW points. The center of this diagram represents the zenith of the observer. So you see the Z, the zenith coming up in the center. Irrespective of where the observer is or where the body is, these 5 points N, E, S, W on the rational horizon and point Z at the center remain at these locations only. Now in this question they have given us the latitude. The latitude is 62 degrees 30 minutes north. So it tells us that the zenith will be the north of the equinoctial or the Q point. Or in other words, the Q point would be south of the zenith. And we know that the arc ZQ, Z to Q represents the latitude of the observer. And this in our case is 62 degree 30 minutes. So from the zenith, I go 62 degrees 30 minutes south, and this is where the equinoctial would pass, and I will have the Q point. So you see the equinoctial is passing from Q point, and the equinoctial always passes from the east and west points. So this WQE, which we have on our diagram now, represents the equinoctial for this particular observer. Now once the equinoctial is there, we can also show the pole. The pole, in this case the observer is in north hemisphere, so we will have the north celestial pole as our elevated pole or visible pole, and the pole is 90 degree away from the equinoctial or the Q points. So from the Q point I go 90 degrees away, and this is the point where I have the pole. Let's represent this point as P. We have the pole in the diagram now. Now the next information which the question tells me is that star Vega bore 270. Now in this diagram, the 270 bearing is represented by line ZW. ZW represents 270 bearing. So Vega has to be somewhere on this line. I don't know the altitude of Vega, so I will pick up any random location here and I will put star Vega in this location. So we have the star Vega in our rational horizon diagram now. Any doubts up to here, beta, before we proceed ahead?
Clear, sir.
Okay, beta. Great.
No.
Very good. Great. Let's move ahead. Now the next information which is given in the question is the unknown star bore north with an altitude of 34 degrees. At the same time, when Vega was sighted, the unknown star was bearing north with the altitude of 34 degrees. Now coming back to our diagram, the ZN line represents the north bearing or 000 bearing. So the unknown star has to be somewhere on this line. Its altitude is given to us as 34 degrees. Now point N is on the horizon. Our star is 34 degrees above the horizon. So from point N going 34 degrees above the horizon, this is where the unknown star is. Let's mark the unknown star as X. So you can see now that all the information what was given to us in the question has been fed in the rational horizon diagram. Now what we do next is I have star Vega in my diagram, and I have the pole, I have the zenith. So I'm going to draw the celestial meridian of star Vega. Its celestial meridian will originate from the pole and it will pass from star Vega extending downwards. So let us show the celestial meridian in the diagram. The maroon color line which you see from P going up to Vega and going further is the celestial meridian of Vega. Now concentrate your attention to the arc P to Vega. P to Vega. Now this arc is basically the polar distance of Vega. Polar distance of Vega. And we know that the polar distance is equal to 90 minus declination. You see, from Vega to the equinoctial, this is the declination, which I'm showing with the help of the laser pointer now. This is the declination of Vega. And we know equinoctial to pole is 90 degrees. So P to Vega has to be 90 minus declination of Vega, and it is called as polar distance. Now we have the date 13th October 92, and we can get the declination of the Vega from the nautical almanac. So once you do 90 minus that, you get the polar distance. This is the value of the polar distance which will be obtained. So we have the Papa Vega side, P Vega side known to us. Now have a look at the PZ Vega triangle. Okay, I have named it as Vega, otherwise this is the PZX triangle. So in this triangle, I'm showing that triangle with the help of the laser pointer now. Now in that triangle you see angle Z is a right angle because star Vega is at 270 bearing. The pole is north of the observer. So the angle Z is 90 degrees in this particular diagram. And in this triangle, we know the side PZ, Papa Zulu side, is known to us. It is the co-lat of the observer, or 90 minus latitude of the observer. The latitude is 6230. So 90 minus that is the side Papa Zulu PZ. That's why it is shown with a green tick. Now we also have the Papa Vega side, which is the polar distance of Vega, 51 degrees 13.1, which we found earlier. Now you see in this triangle Papa Zulu Vega, PZ Vega, it's a spherical triangle. All the three sides are great circles, and it has a speciality. Angle Z is a right angle. So we can apply the Napier's rule in this triangle, and we can find out anything else using these two known values. So I will apply the Napier's rule in this triangle, and what I'm going to find out is this angle P. Let me show that with the arrow in the diagram. This angle P is what I'm going to find out. So using Napier's rule, using the two known parts, I'm going to find out this angle P. Now this angle P is basically the LHA of star Vega. It is the LHA of star Vega. So beta, before we proceed ahead, any doubts you are having till here, please share.
So which will be the LHA, sir, of star Vega?
Beta, angle P which you see here of PZ Vega triangle, it is the LHA.
Okay, sir.
You see, it is the angle at the pole contained between meridian of the observer and the celestial meridian of Vega. So that's LHA Vega.
Yes, sir.
Right. चलें आगे बेटा.
Yes, sir.
Let's go. Now the LHA of star X, if you look carefully, the star X is on my inferior meridian. It is on the other side of the pole. P to N is the inferior meridian of the observer. So anybody on the inferior meridian, its LHA is 180 degrees. So LHA of the unknown star is 180, and the LHA of Vega has been found. This is known to us now. So I can, from this information, find out this angle, which I am highlighting with the laser pointer. And what is this angle? This angle is November Papa Vega. This is the angle which I am talking about. November Papa Vega. And what is this angle here? This angle is LHA of the unknown star minus LHA of Vega. Or you can say it is the difference of R angle between Vega and the unknown star. Angle at the pole contained between celestial meridian of Vega and celestial meridian of the unknown star. So it is the difference of R angle between Vega and this particular star. Now once I know this angle, I know this is the difference between SHA of the star X and the SHA of star Vega also, because this is the R angle, difference of R angle between the unknown star and Vega. So SHA is also a R angle. So whatever is the SHA of Vega plus this angle is going to give me the SHA of the unknown star. So what I am going to do now is I will check the SHA of Vega on 13th October 1992 from the almanac. To the SHA of Vega, I will add up this particular angle and I am going to get the SHA of the unknown star. So we will find out the SHA of the unknown star. Now, to identify a star, along with SHA, we also need its declination. Okay, before I proceed ahead with declination, have a look beta. Let me know if any doubts are there in SHA.
सर आपने ZP वेगा एंगल निकाल लिया, P जो अंदर बन रहा है ट्रायंगल के.
That's right बेटा.
तो हमने 180 से सब्ट्रैक्ट करके बाहर का निकाल लिया. उसके बाद जो ये नेक्स्ट स्टेप लिखा है सर आपने SHA X माइनस SHA वेगा, ये समझ में नहीं आया सर. ये मतलब किस रेफरेंस में लिखा आपने?
ओके बेटा, इसको इस तरीके से समझो, मैं अभी बताता हूँ आपको. जो ये एंगल आपने निकाला है, दैट इज नवंबर पापा वेगा, दिस पर्टिकुलर एंगल. This is the R angle between Vega and star X, correct?
Correct, sir.
Now, if you have SHA of Vega known to you and you add this angle, it will give you SHA of the star because it is the R angle difference between them.
Yes, sir.
Right? That's what we are doing. To the SHA of Vega, we will add this particular angle to get the SHA of this particular star. Right, beta? Clear now?
Yes, sir.
Okay. और बेटा और कोई डाउट अभी तक?
सर जो अपना एंगल पी है ना सर, वो तो अपना पी होगा एरीज प्लस एसएचए, करेक्ट सर? एलएचए एरीज प्लस एचएचए.
एंगल पी यू मीन जेड पी वेगा?
नो, एंगल ZP Vega, yes sir.
Angle ZP Vega is the LHA of Vega. This is what we calculated earlier.
हाँ, तो वो होगा LHA Aries plus SHA Vega.
No बेटा, no. Actually इस diagram में ना Aries नहीं है. If you want, we can make Aries and I can explain it to you from there also. Shall I do that?
But sir,
हाँ सर, वो ज्यादा बेटर है बिकॉज.
ओके, अभी बता रहा हूँ बेटा. जस्ट अ मिनट, गिव मी अ मिनट, आई विल टेल यू. Just a minute, let me take this to the whiteboard. I'm stopping the just do one thing beta. Let me tell you about the declination. Once I tell you about the declination, I'll explain this with Aries also. Okay, let's first finish this,
okay,
then we go to the whiteboard.
One more time starting. Okay.
Okay, all right. So let's now see how do we find out the declination of the unknown star. Concentrate your attention on November to Papa. November to Papa is the elevation of the pole or altitude of the pole. Now we know that the elevation of the pole or altitude of the pole is equal to the latitude of the observer. And we know the latitude is 62 degree 30 minutes. So November to Papa is equal to 62 degrees 30 minutes. November to X-ray, which is the true altitude of the star, is 34 degrees 00 minutes. So I can now easily find out the difference between them. It is going to give me Papa X-ray, PX. So in this case, the PX is going to be 28 degrees and 30 minutes. It is NP minus NX. NP equal to the latitude is 6230. NX, the altitude of the star given in the question, is 34 degrees, giving us Papa X-ray PX as 28 degrees 30 minutes. Now, if you look carefully, Papa X-ray PX is the polar distance of this particular star. Now, we know polar distance is 90 minus declination. So once we have the polar distance, 90 minus the polar distance is going to give us the declination of the star. So we can obtain the declination of the star. Since it is the polar distance from the North Pole, the declination will have a northerly name. It is close to the North Pole, so the declination of the star is north. So once we find the SHA and declination, SHA comes out to be 195.33 and declination comes out to be 61 degree 30 minutes. We can go to the star information table on page 268, look for this SHA 195.33, match the declination, and we can identify the star as Dubhe. So this is how we solve this question. So used the same principle, put all the information in the rational horizon diagram, applied the spherical trigonometry, Napier's rule, and we were able to find out the SHA and declination of the star, identifying it. So beta, any doubt in the declination?
सर अगर SHA और जो वैल्यू हमने निकाली है उस पे एग्जैक्ट मतलब वो कोई स्टार नहीं आ रहा, पॉइंट्स में कोई डिफरेंस आ रहा मिनट्स में, तो फिर वही वाला ले सकते हैं क्या?
Okay, beta, okay, I'll tell you. Whenever you get a star identification question and you get the SHA and declination from the question and you match it, there can be a bit of difference between your values and the values given in the table. That difference is basically because the position which we are using in these calculations are our DR positions, dead reckoning positions. So because of that, some slight error can be there. So you pick up whatever the nearest value is available in the table, you pick up that particular star and take that as your answer.
Okay, sir.
Yes, sir. इसमें भी डूबे का 194 कुछ आ रहा है.
Yeah, that's okay, beta. That's okay. You pick up the star which is having the nearest values which you calculated.
Sir.
Go ahead, beta.
Extremely sorry, sir. I lost track. So just 3 steps I'm going behind. So we get the value of P from the PZX triangle, right?
Yeah, PZ
The
Vega
P
triangle.
of Vega triangle will get from so uske
Alpha. Now moving on to the next question. Let's go.
ये भी हो गया सर.
Beta, moving on to the next one. Let's now move on to the next question.
We completed this question, sir.
Okay, that's right. Just a minute. On Let's move on to the next question now. For a stationary observer, the true altitude of an unknown star when bearing south was 14 degrees 11.2 minutes. 1 hour and 7 minutes later, the true altitude of star Betelgeuse, having a SHA 271 degrees 17 minutes, declination 7 degrees 24.5 minutes, when bearing north was 47 degrees 25.5 minutes. Identify the unknown star. So let's try to put all this information in the rational horizon diagram. At a certain point, the unknown star was bearing south. The altitude was 14 degree 11.2. So after that, the observer waited for 1 hour and 7 minutes. And after this much time, he observed that star Betelgeuse was bearing north with a altitude of 4725.5. So we need to identify the unknown star. Let's make the rational horizon diagram. We have the rational horizon, points N, E, S, W marked. Let's mark the center as the zenith of the observer. We have the zenith on the diagram now. The information given in the question is unknown star was bearing south. That means line Z to S, south bearing, and altitude 14 degrees 11.2. So from the horizon, which is point S, we are 14 degrees 11.2 minutes away. So let's mark 14 degrees 11.2, and this is where the unknown star is. We have the unknown star in our rational horizon diagram. Now 1 hour 7 minutes later, the star Betelgeuse was bearing north. North bearing is Z to N, and the altitude of star Betelgeuse was 4725.5. So N point on the horizon, 47 degrees 25.5 minutes away from it. 4725.5 is where we have Betelgeuse. So we have the Betelgeuse also in our rational horizon diagram. Now, on this particular day, the declination of Betelgeuse was 7 degrees 24.5 minutes north. In other words, Betelgeuse is 724.5 north of the equinoctial. Now this tells me equinoctial is 7 degrees 24.5 minutes south of Betelgeuse. So from star Betelgeuse, I go 7 degrees 24.5 minutes south, and this is where the equinoctial should be passing. So I get my Q point, and I know the equinoctial will pass from Q. Equinoctial always passes from the west and east points. So I can now mark off the equinoctial in the diagram as WQE. WQE is the equinoctial. Now I can easily find out the arc Z to Q. I know what is N to Betelgeuse. It is 4725.5. I know Betelgeuse to point Q is 724.5. And I know N to Z is 90 degrees. 90 degrees is the radius of this diagram. So 90 minus 4725.5 minus 724.5 gives me ZQ, which is 35 degrees and 10 minutes. So this 3510 is the latitude of the observer. ZQ is the latitude of the observer. So observer's latitude is 35 degrees 10 minutes south, because you see the zenith is south of the equinoctial. So 35 degrees 10 minutes south is the latitude of the observer. So beta, before we proceed ahead, any doubts up to here?
सर ये एक बार डेक्लिनेशन का बताना सर.
Okay. Beta, the declination of star Betelgeuse is given to be 7 degree 24.5 minutes north, right?
Right, sir.
Now we have fixed up Betelgeuse in our diagram. Correct? Betelgeuse is on a northerly bearing at a altitude of 4725.5. So Betelgeuse is fixed up. Now Betelgeuse is 7 degrees 24.5 north of the equinoctial. That means equinoctial has to be 724.5 south of Betelgeuse. Did you get that, beta?
No, sir.
Okay, listen again, once again. Betelgeuse is 7 degree north of the equinoctial. Correct?
Yes, sir.
So equinoctial has to be 7 degrees south of Betelgeuse.
Yes, sir. Yes, sir.
Got it now, beta?
Yes, sir. Yes, sir.
And you can see here in the diagram also, Betelgeuse is at 7 degree north declination and it is 7 degree north of the equinoctial from the Q point. So it fits in with.
Okay, sir.
Okay, great.
Okay.
Any more doubts up to? Okay, let's go ahead then. Now once I know the latitude, I can mark off the pole also. The pole is 90 degree away from the equinoctial and it has to be somewhere here. So this is where the pole is, and I know that the elevation of the pole or altitude of the pole, in this case S to P is the elevation of the pole. It has to be equal to the latitude of the observer, which is 35 degree 10 minutes. So S to P is 35 degree 10 minutes. S to the particular star is 1411.2. Now this helps me to get the polar distance of the star P to this particular star. It is 3510 minus 1411.2 and 20 degrees 58.8. So I get the polar distance of the unknown star, and 90 minus polar distance gives me the declination of this particular star. The declination will be south because we can see the star is 20 degrees away from the south pole. So 90 minus this gives me the declination. I get the declination of the star as 69 degrees 1.2 minutes south. So before proceeding ahead, any doubts up to here, beta?
Sir, can you explain the direction of the declination, sir?
Okay. Now always remember, beta, whenever you see the pole south of the zenith, it is always the south pole. So is that clear that pole is south?
Yes, sir.
Now if you are 20 degrees away from the south pole, are you in the southern hemisphere or north hemisphere?
Southern.
So that tells you why the name of the declination is south.
Yes, sir. Got it.
So all doubts, beta?
सर बट अगर पी जेड के काफी पास होता हो फिर हमें 20 डिग्री मालूम होता तो वो नॉर्थ में भी जा सकता है साउथ में भी जा सकता था ना फिर से
नहीं बेटा, पी जेड के किसी भी पॉइंट पे हो, आपको इतना तो पता चल ही जाएगा ना कि ये जेड के साउथ में है या नॉर्थ में है.
हाँ जी सर, जेड साउथ नॉर्थ मालूम चल गया सर.
Right. So wherever the pole is, if it is south of the zenith, it has to be the south pole. If it is north of the zenith, it has to be the north pole. So basis that whichever pole you identify, the declination will be having that name only.
Okay sir. Yes, sir.
Okay. Okay.
But
so yeah.
अपना जेड सॉरी पी अपना ऊपर होता है जेड के, ठीक है, और एक्स अपना नीचे होता है जेड के, तो फिर साउथ होता है ना सर वो?
नो बेटा, पी अगर जेड के ऊपर है तो दैट मींस दैट पी इज द नॉर्थ पोल.
हाँ जी सर.
राइट. नाउ एक्स कैन बी नॉर्थ ऑफ जेड और साउथ ऑफ जेड, दैट डज नॉट अफेक्ट द डेक्लिनेशन एट ऑल.
अच्छा अच्छा समझ गया सर.
ओके, चलें बेटा, आगे चलें.
यस सर.
वेरी गुड, लेट्स गो. Now let's draw the declination circle of the unknown star. The star is here. The declination circle will pass from the position of the star and it will be centered at the pole. So we have the declination circle of the star in our rational horizon diagram. The star will be moving in the direction of the arrow, like this. The star will be moving in this particular direction. Now, whenever you want to check the direction in which the body will be moving, consider that we have a celestial body on the equinoctial. Now that celestial body will be rising at point E, moving along the equinoctial, and it will be setting at point W. All the bodies rise on the eastern horizon and they set on the western horizon. So whatever direction this body is moving on the equinoctial, the same direction will the declination circle have. The star is also going to move in this particular direction only. So that gives us the direction in which the star is moving. Clear, beta? This one is clear?
Yes, sir.
Okay, beta. Great. Now the question told us that when we observed the star, the next observation was taken 1 hour and 7 minutes later. Betelgeuse was observed 1 hour 7 minutes later after the observation of this unknown star. So let us now try to see, after 1 hour and 7 minutes, where will the unknown star be? Unknown star will be moving in this particular direction on its declination circle. Now we know that stars cover their R angle at a rate of 15 degrees 2.5 minutes. So in 1 hour and 7 minutes, the star is going to cover an R angle of 16 degrees 47.8 minutes. So let me show this R angle in the diagram now. From this position, the star is going to move in this direction by an amount of 16 degrees 47.8 minutes. So this is where the star is going to be. Now let me draw the celestial meridian of the star. We name the star as X, and P2X represents the celestial meridian of this particular star. Now once I have the celestial meridian on the diagram, I can now also easily find out angle ZPX. Pay your attention to this particular angle, ZPX. We can easily find out this angle as 180 minus the R angle of the star. So 180 minus 1647.8, 180 minus 1647.8 gives me the angle ZPX as 163.12.2 minutes. So let's mark it in our diagram. This is the angle which we have found now, and this angle is 163 degrees 12.2 minutes. Now if you look carefully in the diagram, this is the pole and this is star Betelgeuse. This is the celestial meridian of star Betelgeuse. PZQN is the celestial meridian of star Betelgeuse. And the celestial meridian of the unknown star is PX. Now if you look carefully, this unknown star is 163 degrees 12.2 minutes east of Betelgeuse. This is where Betelgeuse is. If you go in the easterly direction, see this is the easterly direction. So from Betelgeuse, if you go in the easterly direction by an angle of 163 degrees 12.2 minutes, you reach up to the unknown star. Or in other words, the unknown star is 163 degrees 12.2 minutes east of Betelgeuse. So this tells me that the SHA of the unknown star will be SHA of Betelgeuse minus 163.12.2. Why there is a minus here? Because SHA is a westerly measurement. SHA is measured in the westerly direction. If the star was west of Betelgeuse, we would have added this angle. But the star is east of Betelgeuse, so we have subtracted this angle from the SHA of Betelgeuse. It will give us the SHA of the unknown star, which comes out to be 108 degrees 4.8 minutes. So SHA of Betelgeuse is available to us from the almanac. Minus this value gives me 108 4.8, which will be the SHA of the unknown star. So now I have the SHA of the unknown star as well as the declination of the unknown star. Using these two values, if I go to the star table on page 268, I can easily look out for the star and it comes out to be Atria. So the unknown star is Atria. So you see we followed exactly the same approach. We put all the information in the rational horizon diagram and we got the answer. We got the unknown star. So beta, have a good look at the diagram. Let me know your doubts.
So can you explain the SHA star X, please, sir, once more?
Okay, beta, okay. Now beta, if you look at the diagram, is it clear to you that this star, unknown star, is 163 degrees east of Betelgeuse?
Yes, sir. That is
right?
NPX, right?
Yeah, the angle NPX is 163 degrees. So we know that this unknown star is 163 degrees east of Betelgeuse, right?
Yes, it means that is a difference in our angles, right, sir? From the
Exactly, beta. It is the difference in our angle between these two, and the star is east of Betelgeuse. Now, SHA is a westerly measurement. It is measured in the westerly direction. If you go in east, the SHA would decrease. So that means the SHA of this particular star would be 163 degrees lesser than the SHA of Betelgeuse because it is east of it. So that's why we found out the SHA of the star by using SHA Betelgeuse minus 163 degrees.
So the celestial meridian of Iris will come on west side, right, sir?
Okay, you want to fit Aries here?
Yes, sir.
Okay. ठीक है बेटा, वो भी कर. No, it is not easterly, not easterly. You see, this direction is westerly direction. Huh? Always see the direction when it is crossing your meridian. Okay, this is westerly direction. When you look at Earth from the South Pole, the westerly direction is anti-clockwise. When you look from top of the North Pole, the westerly direction is clockwise.
Okay.
Okay, so this blue angle which you see is the SHA of the unknown star. Now let me show you the SHA of Betelgeuse also. Let me show this in red. SHA of Betelgeuse is going to be this particular value up to here. So this pink color angle which I have shown, this one, is the SHA of Betelgeuse, and the blue color angle here is the SHA of the unknown star. Let me erase the unnecessary lines. So SHA of Betelgeuse minus 163 degrees will give you the SHA of the unknown star.
Yes, sir. I'm got it. Understand.
Okay.
Yes,
so ओके बेटा, ऑल राइट. हाँ बोलो बेटा.
सर इट वुड हैव बीन बेटर अगर इसमें एरिस को हम जो बेटलगीज के रिस्पेक्ट में एरिस दिया 271 डिग्रीज, दैट इज
Yeah, right.
व्हेन इट इज इन द नॉर्थ पोल, तो हम वो ईस्ट वाली साइड से थोड़ा सा ऊपर बनाएंगे 271 डिग्रीज, है ना?
ओके बेटा, ठीक है, एग्जैक्टली बना देते हैं.
तो
I'll
वहां
show
से मैं समझ गया सर, लेकिन वहां के रेफरेंस में अगर साउथ पोल दिखाते तो आई थिंक दोनों चीज एक साथ हो जाती.
ये रहा. SHA of Betelgeuse is 271. Okay, so let us try to fit it there. Let me remove these. So from Betelgeuse, if I go 271 degrees east, that is where Aries would be. So from here, okay, I'm going 271 degrees. So up to here 180, up to here 270, 271, maybe somewhere here. So this is where the celestial meridian of Aries would be, somewhere here. Let me show Aries. And this pink angle is 271. This is the exact value of SHA of Betelgeuse. Now let me show you the SHA of the unknown star. Let us show it with blue color. SHA of the unknown star will be this angle up to X. And the difference between them 163, 12.2.
सर ये 271 आपने साउथ पोल के रिस्पेक्ट में प्लॉट किया ना क्लॉकवाइज?
That's right, beta, because we have the South Pole, so we'll have to plot everything with respect to South Pole.
ये नॉर्थ में था ना, तो मुझे लगा आई वाज प्लॉटिंग दिस साइड, देन डिफरेंस सेम आ रहा है बट मैं अलग तरीके से प्लॉट कर रहा था.
Okay. ओके, सो और बताओ बेटा, और क्या डाउट आ रहा है?
Nothing, sir.
Very good, great. So you have an idea now how these questions look like. Star identification के क्वेश्चन हमने कर लिए हैं. These are basically the PZX triangle based questions. So shall I remove the presentation now?
Yes, sir.
Okay, great. Okay, so beta, I'll be giving you a few more questions also in an assignment, which will have this PZX triangle concept. So please practice those questions also. So that was our PZX triangle question. Now we are moving on to our next topic. So this is one topic which comes in question number 8 and 9, rational horizon diagram, PZX triangle. Some other topics which come in those 8 and 9 questions are questions based on stellar magnitude, questions based on Kepler's laws of planetary motion. So I'm going to show you what type of questions come based on those topics. So shall we go into that presentation?
Yes, sir.
Okay, let's go. So बेटा, पहले मैं आपको एक स्टेलर मैग्नीट्यूड का क्वेश्चन दिखा रहा हूँ. दिस इज अ टिपिकल क्वेश्चन विच हैज कम इन आवर पेपर्स. सो इस क्वेश्चन में एक स्पेशल कॉन्सेप्ट यूज होता है, दैट इज द लॉगरिथमिक कॉन्सेप्ट. सो लेट अस सी दिस क्वेश्चन फर्स्ट. Now the first concept which we are going to look into is the concept of stellar magnitude. Now we are aware stellar magnitude is basically a scale which gives us the apparent or relative brightness of different celestial bodies. Let's see the question. The question says star A has a magnitude of minus 0.8 and it is 30 times brighter than star B. Find the magnitude of star B. Now, all these questions which we are discussing are picked up from the past papers. So let us see how do we attempt this question. Now, for doing this question, we need to be aware of two things. Number one, that the stellar magnitude gives us a formula or a relationship with which we can find out how many times a particular body is brighter or dimmer than the other body. What is that formula? The number of times a star is brighter than the other is given by the formula 2.51 raised to power the difference of their magnitudes. So this is the formula which we will be using in this question. Now, second concept which we need to be aware of, which we have done in our school time, that is a logarithmic concept. That formula, logarithmic formula, is log of a raised to power b is equal to b multiplied by log of a. So this is a logarithmic formula which we will be using, which we need to use to solve this particular question. So once we are aware of these two things, the question can now be solved. First of all, let's assume that the difference of magnitudes between the two bodies is x. If the difference of magnitude between the two stars, star A and star B, is x, that tells us 2.51 raised to power x should be equal to how many times one star is brighter than the other. Now this is given to us in the question. The question says that star A is 30 times brighter than star B. So this tells us 2.51 raised to power x is equal to 30. Now we want to solve this relationship for x. So for this, what we do is we take a log on both the sides. So this gives us log of 2.51 raised to power x is equal to log of 30. Now applying the logarithmic formula which we saw, log of a raised to power b is equal to b multiplied by log a. Similarly, you see log of 2.51 raised to power x is equal to x multiplied by log of 2.51, and this is equal to log of 30. Now keeping x on one side and taking the other items on the opposite side, we get x is equal to log 30 upon log of 2.51. We can easily solve this using our scientific calculators. So when we solve this for x, it gives us the value as 3.6958. So this x, which was assumed to be the difference of magnitude between star A and B, has been found to be 3.6958. Now it is given that the magnitude of star A is minus 0.8. The difference is 3.6958. And since star B is dimmer, it is given in the question, star A is 30 times brighter than star B. So this tells us that the star B is a dimmer star. Now, since it is dimmer or less bright, its magnitude number will be greater than the magnitude number of A. We know that the stellar magnitude scale is a reverse logarithmic scale. That means as the brightness increases, the magnitude decreases. And as the brightness goes down, the magnitude number increases. So this tells us that star B, which is dimmer, its magnitude number should be greater than the magnitude of A. So magnitude of A was minus 0.8. The difference between the two is 3.6958. This is the difference between magnitudes of A and B, and magnitude of B has to be greater than the magnitude of A. So what we do is we add this difference 3.6958 to the magnitude of A, which is minus 0.8, giving us a value of 2.8958. So this is the magnitude of star B. So you can see now star B magnitude 2.8958, star A magnitude is minus 0.8. The difference between both of them is 3.6958, and if you use that difference in this equation, 2.51 raised to power this difference, it will give you the value of 30. So this is how the question is solved. So any doubts in this beta?
No, sir.
Sir, 2.51 raised to 2.8958 की वैल्यू 30 आनी चाहिए ना?
नहीं बेटा, 2.51 raised to 3.6958. This is the difference, huh?
Okay.
So you can try that out. Just punch in the calculator and see if it comes to 30.
एंटी लॉक करना पड़ेगा ना?
नहीं, कुछ एंटी नहीं कर पाएगा भाई, ऐसे आ रहा है वो तो 2.51 के ऊपर 3.6958 की वैल्यू 30 आ जा रही है।
बेटा एक ही काम करना पड़ेगा, अपने कैलकुलेटर में लॉग का बटन कहाँ है वो ढूंढना पड़ेगा।
यस सर, यस सर, यस सर, इट्स ओके सर।
हाँ, और एक और चीज अब तुम्हें बता दूं मैं कि तुम्हारे कैलकुलेटर में, इफ दे आर गुड साइंटिफिक कैलकुलेटर, 2 लॉग होंगे। एक होगा लॉग टू द पावर, लॉग टू द बेस ई, एक होगा नेचुरल लॉग। सो दोनों में से कोई भी लॉग यूज कर सकते हो आप। बोथ ऑफ देम विल गिव यू द सेम वैल्यू। ओके, सो बस वो बटन ढूंढ लेना बेटा, दैट इज द ओनली प्रिकॉशन। If you want, you can punch in these numbers and see if you get the answer.
आ रहा है सर, आ रहा है। एक ही लॉग।
Got sir, got it.
Okay, great. Very good. So this is a typical question which has come. So now you know if this comes, how it is to be done. चलें बेटा आगे।
Sir, is there any application for these questions, sir, or it will be same like direct?
No beta,
What
no
is
application, no application. They are pretty simple and straightforward. So this was a little tricky because of the log formula. Otherwise, these are very simple questions.
Oh, okay.
Okay, so moving ahead now. Now moving further, the next set of questions is based on Kepler's laws of planetary motion. So there are 3 laws which basically give us an idea about the motion of planets around the sun in the solar system. So before we go into the numerical, let us discuss about Kepler's 3 laws of planetary. The first law of Kepler states that all the planets revolve around the sun in elliptical orbits. So as you can see, we have this blue color planet revolving around the sun in an elliptical orbit. The green color orbit which we see in the diagram is having elliptical shape. Now before Kepler, people used to believe that the orbits of planets are circular. But Kepler's, with his observations, proved that these orbits are not circular but elliptical. Though the ellipticity of these orbits is very, very less, they are very close to a circular shape, but still they are not exactly a circle. They are not exactly circular. They are actually elliptical. Now, just as a circle has one center, the ellipse, on the other hand, has 2 reference points. and these reference points are known as focus. So it has focus 1 and focus 2. In plural, it is known as foci. So all the planets revolve around the sun in elliptical orbits. Every elliptical orbit has 2 foci, and sun is situated at one of the foci of the ellipse. The other foci is blank. There is nothing there, but sun is situated at one of the foci of the elliptical orbit of all the planets. This is Kepler's first law. Any doubts, beta?
Negative, sir.
Very good. Now moving on to Kepler's second law. Kepler's second law states that the radius vector of a planet sweeps out equal areas in equal intervals of time. Let us understand with the help of a diagram. We see the sun as the yellow circle in the middle of the diagram, and then we see a elliptical orbit of a particular planet, and in this elliptical orbit, let us assume that on a particular day when we started our observation, the planet was at this particular location. You can follow the laser pointer. So let us assume that on one particular day when we started observing the planet was at this particular location where the laser pointer is right now. Now, if the planet is at this location, the radius vector of the planet is this one. You can follow the laser pointer. This is the radius vector of the planet. Now, after that, the planet starts to move. We keep on observing the planet day after day. And let us say after 30 days, we again make our observation and the planet has reached up to here. Now, in this interval of 30 days, the radius vector of the planet has covered an area which is shaded in blue. This is the area swept by the radius vector of the planet in a duration of 30 days. Now, after this, the planet, we stop our observation. The planet keeps on moving on its orbit. Now, when you are moving on an elliptical orbit, at some places you will be far away from the foci, which is basically the sun, and at some places you will go closer to the foci. In a circle, all the points on the circumference are equidistant from the center, but in an ellipse, the track of the ellipse sometimes goes closer to the foci, to a particular foci, and sometimes goes away from the foci. So the planet moves further and it reaches at this particular location where the laser pointer is right now on a certain day, and we start our observation again. Now we start our observation. This is the radius vector of the planet right now. The planet continues to move and we keep observing the planet for the same duration of 30 days. Now, after 30 days, we observe that the planet has reached up to this particular point. And you can see this is the radius vector of the planet now. The area which is swept by the radius vector of the planet in the same duration of 30 days is represented by this blue color sector. So you can see the two different sectors as the areas swept out by the radius vector of a planet during its two different locations in its orbit. Now Kepler said that the area swept out by the radius vector of the planet in equal intervals of time will be equal. So the area of this blue sector will be equal to the area of this blue color sector. Both their areas are going to be same. Now, what does this tell us about the motion of the planets in its orbit? Now, if the planet has to sweep out equal areas in equal intervals of time, the planet will have to move faster in its orbit when it is closer to the sun. You see, at this particular location, the planet is much closer to the sun as compared to the previous observation. So with the planet being much closer to the sun, you see the length of the radius vector is much smaller as compared to the previous case. Now with the length of radius vector being much smaller, if it has to sweep out equal area, it has to move at a much faster pace or much faster speed in its orbit. Now, when the planet is far away from the sun in this particular condition, you can see the radius vector is very, very long as compared to the radius vector in the previous instance. Now, with the radius vector very, very long, if it has to sweep out equal area in equal interval of time, the radius vector of the planet has to move very slowly in this part of its orbit. So, it gives us an indication that the planet moves faster when it is closer to the sun. You can see this is the sector where it is closer to the sun, and the planet has moved quite fast in its orbit. And when the planet is far away from the sun, it will move very slowly as compared to the previous instance. So the motion of the planet, or the speed with which it covers its orbit, is not constant or fixed. The planet keeps on changing its speed. It becomes slow when it is far away from the sun, and it gains speed, it picks up speed and becomes faster when it is closer to the sun. So this is Kepler's second law of planetary motion. The radius vector of a planet sweeps out equal areas in equal intervals of time, indicating to us that the planet will be moving faster in its orbit when it is closer to the sun, and it will be moving slower in its orbit when it is farther away from the sun. So, any doubts, beta?
No, sir.
Very good, beta. Great. Now moving on to Kepler's third law of planetary motion. Kepler's third law basically gives us the relationship between the mean distance of a planet from the sun, which is also known as its orbital radius, represented by alphabet R, and the time it takes to complete one revolution around the sun, which is also known as its orbital period, represented by alphabet T. So the third law gives us a relationship between the orbital radius and the orbital period of a particular planet. What does the law say? The law says that the square of a planet's orbital period is proportional to the cube of the mean distance of the planet from the sun. In other words, T square is proportional to R cube. It can be denoted in this particular relationship. T square upon R cube is constant, can be considered as K. T is the orbital period of a planet. Let's say, for example, if you take the case of the Earth. So in the case of Earth, the orbital period is 365.25 days. and r is the orbital radius, mean orbital radius of a planet. In case of Earth, the mean orbital radius of the Earth's orbit around the Sun is 93 million miles, or 93 into 10 raised to power 6 miles. So this is the relationship given by Kepler's third law of planetary motion. T square by r cube is equal to constant. This is a very important relationship, and we get numerical question based on this particular relationship. Clear, beta? Any doubts?
No.
Very good. Now, how can we utilize this relationship in the numerical questions? Now, for using this relationship, we need to be aware of the orbital time, or the time Earth takes to complete one orbit around the Sun, and the orbital radius of the Earth. Now, we know that the time period, orbital time period of the Earth is 365.25 days. And we know the orbital radius of the Earth is 93 million miles, which is 93 into 10 raised to power 6 miles. So T square upon r cube of Earth converts to 365.25 square divided by 93 into 10 raised to power 6 cube. This being constant for each and every planet should be equal to T square by r cube of any of the planets of the solar system. If you look carefully now in this relationship, T square by r cube of Earth is known to us. If we are given the orbital radius or the orbital time period of any of the planets, one of these two items is provided to us. By using this relationship, we can easily find out the second unknown item. If the orbital time period of a planet is given, we can put that in this relationship and we can obtain its orbital radius. And the opposite is also true. If they provide us with the orbital radius of a particular planet, we should be able to calculate the orbital time period of that particular planet. Now for this, you need to be aware of these two values, the orbital time period of the Earth, 365.25 days, and the mean orbital radius of the Earth, 93 into 10 raised to power 6 miles. These figures are not given in the question. It is expected that the candidate is aware of these figures to be used in a numerical based on the Kepler's laws. Clear,
तो
बेटा?
स्क्वायर अपना कांस्टेंट है वो हर प्लेनेट का अलग होगा ना सर?
Say again, beta.
This ratio T square upon R cube equals to constants. Then this constant will be different for different planets.
No, beta, it is the same for all the planets. That's why it is called constant, huh?
Okay, sir.
So you take the T and R of any planet, and when you put it in this relationship, it will give you the same value.
Okay, sir.
Okay. चलें बेटा, आगे चलें. Okay, let's go. Now, next we refer to some planet configurations. Configurations basically means a particular location of the planet in its orbit. So the terms which are used to represent or show planet configurations are conjunction, number 2 opposition, and number 3 quadrature. They basically tell us about the position of a planet with respect to the sun. Let us now understand all these 3 configurations or all these 3 terms with the help of a diagram. Let's show the sun in our diagram. Then around the sun we show planet Earth. I have shown it in blue color. Our Earth is a blue planet. And let's show the orbit of the Earth now. We have the orbit of the Earth on the diagram. Now let's show another planet of the solar system. We show the red planet, and it is the Mars planet. We are aware that the orbit of Mars is greater than the orbit of the Earth. So let's now show the orbit of the Mars. We have the orbit of the Mars in our diagram. Now both Earth and Mars are revolving around the sun in their orbits. The speed at which they are revolving around the sun is different. They are revolving around the sun with different speeds. All the planets have different speeds. We just saw the third law of Kepler's planetary motion, which said t square by r cube is equal to constant. So as the radius keeps on increasing, the time period also keeps on increasing. So that tells us that the angular speed with which the planets revolve around the sun will also keep on changing from planet to planet. Now with varying speed, it is possible that the Earth and a particular planet may be at different locations with respect to the sun. Like for example, right now when you see in the diagram, you can see that for an observer on the Earth, the sun as well as the planet Mars are in the same direction. Both the sun and planet Mars are in the same direction. Any doubts, beta? Okay, all right, maybe some disturbance. Let's continue. Now this particular placement of the planet with respect to the sun is called as conjunction. We say that this particular planet or planet Mars is in conjunction with the sun. So this is the meaning of the first term, which is conjunction. Basically means that the planet is in the same direction as the sun. The planet is in conjunction with the sun. Now let's say after some time we keep on observing this particular planet, and this particular planet moves to a different placement in its orbit, and right now the planet has moved to this particular placement, this particular location in its orbit. Now for an observer on the Earth with the planet Mars at this particular location, you can see now that the sun and the planet Mars are opposite to each other, or they are in opposite directions. The sun is in one particular direction and the planet Mars is exactly in the opposite direction. Now this particular orientation is called as opposition. We say the planet Mars is in opposition to the sun. So opposition basically means that that particular planet and the sun are in totally opposite directions. Now let's assume that the planet keeps on moving in its orbit with some relative speed, and at another particular instant we observe that the planet Mars is at this particular placement or location in its orbit. Now, if you observe this planet Mars carefully, you see the direction in which the planet Mars is at right angles to the direction in which the Sun is. So whenever a planet is at right angles to the direction in which the Sun is, it is called as quadrature. So this is the planet Mars in quadrature. The direction in which the planet Mars is 90 degrees away from the direction in which the Sun is. Now there is a possibility, another possibility of quadrature. If the planet Mars at a particular instant reaches to this location in the diagram, you can follow the laser pointer. So at this particular location also, the direction in which the planet is at right angles to the direction of the Sun. So it tells us that this particular planet is in quadrature with the Sun. So conjunction means the Sun and a particular planet are in the same direction or the angle between them is 0. Opposition means that the direction in which the Sun and a particular planet are exactly opposite to each other, or the angle between the Sun and that particular planet is 180. And quadrature means that the direction in which the Sun is 90 degrees away from the direction in which the planet is, or the angle between the Sun and the planet is 90 degrees. Now these terms are important from the point of view that whenever we get numerical based on Kepler's laws of planetary motion, sometimes these concepts are used in the question. So we should be aware of what these terms means to accurately solve that particular question. So this is the importance of understanding these terms. Any doubts, beta? Very good, beta. Great. Now the next important concept which we have is the concept of elongation. Let's understand what elongation is. Elongation of a planet is the angle at the center of the Earth between the Sun and that particular planet. Let's try to understand it with the help of a diagram. We have the Sun in our screen now. Let's show the planet Earth. We can also mark off the orbit of planet Earth. You can see the orbit of Earth in blue color. Now let's show another planet. In this case, we show planet Venus. Now Venus is closer to the Sun as compared to the Earth. So let's now mark off the radius of the orbit of Venus also. You can see the orbit of Venus in maroon color as shown by the laser pointer. Let's now try to show the radius vector of Venus as well as Earth. So you can see this dotted line joining the center of Sun with the center of the Venus. This marks off the radius vector of planet Venus. Similarly, you can see this blue color dotted line showing the radius of the Earth. Now let's draw another line joining the center of the Earth and the center of the planet Venus. So you can see this red color line joining the center of Earth with the center of Venus. Now from this diagram we can easily understand what elongation is. You see this red highlighted angle in the diagram is what is elongation. Let's try to match with the definition of elongation. The definition says elongation of a planet is the angle at the center of the Earth. You see this red angle is being made at the center of the Earth between the Sun and the planet. So from the center of the Earth, a line joining the center of the Sun and a line joining the center of the Venus, angle between those two lines is the elongation. So angle at the center of the Earth contained between the Sun and that particular planet is known as the elongation of that particular planet. Now, as Earth and Venus are moving with different orbital speeds, different angular velocities in their orbits, their location with respect to each other will keep on changing. The planet Venus could be at any particular elongation depending upon what is its position in its orbit. Let's assume that if planet Venus is at this particular position here, the elongation will be the blue color line showing the radius of the Earth and the line joining the center of the Earth with the location of Venus at this particular point. If Venus is at this particular location here, the elongation will again be by the angle between the radius of the Earth and the line joining the center of Earth with center of the Venus. Now, if you look carefully, that as the planet Venus moves in its orbit, you can follow the laser pointer. At this particular point, Venus will be in conjunction with the Sun, or the elongation will be 0 degrees. Now, as it moves in its orbit, the elongation will start to increase. At this particular point, at the first location, it will have a certain elongation. After this, the elongation will keep on increasing. Now, if you look carefully, at this particular point, Venus will have the maximum elongation. The angle at the center of Earth will be maximum at this particular placement of Venus in its orbit. As Venus moves forward in its orbit, you see the elongation will start to reduce again. Now, this point where the maximum elongation occurs, if you look carefully, you will see it is the point where from the center of Earth, if you draw a tangent to the orbit of Venus, the tangent meets the orbit of Venus at this particular point. This is the point where Venus is going to have maximum elongation. And we are aware that the tangent is always perpendicular to the radius of a circle. So this line joining the center of Earth with the center of the Venus, the red dotted line, represents a tangent, and this line joining the center of Sun with the center of Venus represents the radius of the Venus. So they will be at right angles. So this angle here at planet Venus will be 90 degrees. So this is the point of maximum elongation of Venus, and we know at the point of maximum elongation, the angle made at point Venus between the Sun and the Earth would be 90 degrees. Now, this particular diagram is used in solving some of the questions. So you should be clear about the concept of maximum elongation and what is this angle which is made at the planet at the time of maximum elongation. Now, if you consider a exterior planet means the planet whose radius is greater than the radius of the Earth, like say for example Mars. Now, the maximum elongation of Mars is going to be 180 degrees. The maximum value of elongation is possible, which it can be, is 180 degrees. For an exterior planet like Mars, it can reach up to its maximum elongation, that is 180 degrees when it is in opposition to the Sun. But for an inferior planet like Mercury or Venus, the maximum elongation will be less than 90 degrees, and it will depend upon the radius of that particular planet and the radius of the Earth. Now, inferior planets like Venus, as you see in this diagram, can never be in opposition to the Sun. They can never be in opposition. Irrespective of whichever position they are in their orbit, they can never go in a direction which is opposite to the direction of the Sun. And at the same time,